In the design, development, and validation of autonomous vehicles, safety is of paramount concern. This means designers and engineers must consider and test a variety of overlapping systems and subsystems. Each is mission-critical to the automobile's safe operation. ANSYS has developed a comprehensive solution to address the system safety analysis, safe software development, and systems validation with high-fidelity physics-based simulation of the virtual world, traffic scenario descriptions, and sensor simulation. The following demonstration showcases the ANSYS autonomy solution. In this video, we show the development and validation of an autonomous driving system that is designed to keep the vehicle safely operating in city and highway driving conditions. Chapter 1: Functional Safety and SOTIF Analysis. We begin by defining the architecture of the system. Next, we need to ensure that the system is safe and takes into account varying traffic situations, along with system limitations and disturbances. Lives depend on it. This is the role of functional safety analysis and the recent Safety of the Intended Functionality SOTIF standard, ISO 21448, which deals with hazards that emerge from limitations, weaknesses, and disturbances that are not failures, but can equally lead to hazards under some unfavorable triggering conditions. The architecture and safety analysis are synchronized throughout the entire process. First, we discover any hazards associated with the AV function. One identified hazard is collision or too short distance to the vehicle in front, which is rated as unacceptable. At first, we do not know yet what could be possible causes for this hazard, but we're going to find out using causal analysis. A fault tree is a means to identify causes leading to the hazard. Knowing the causes enables systematic development of safety requirements. Either the system must be improved to prevent failures or weaknesses from causing the hazard, or the operation domain of the automated function must be restricted to ensure safe operation. The reasons for this hazardous behavior can be either failures, which has always been the scope of traditional functional safety analysis, or sensor and algorithm limitations or disturbances. For instance, limited contrast resolution of a camera, in combination with triggering conditions like various weather conditions or the glaring sun. To discover and mitigate these reasons that are not failures is the domain of SOTIF. With SOTIF capabilities, we can now use modeling elements like limitation or triggering condition in any sort of safety analysis, just like we used to do with failures in the past. The triggering conditions that we discovered by causal analysis are the input we need for closer evaluation by simulation. Still, there may be edge cases that would probably not be found even by thorough safety analysis. We provide solutions to discover such edge cases automatically, easily scanning through large unlabeled datasets from road testing or simulation campaigns. We are guided to the suspect scenes automatically to perform a manual review and assign the potential problem sources. Results are imported back into our functional safety analysis as new triggering conditions. The edge cases are converted to malfunction behavior in the model. The suspect causes are converted to triggering conditions according to SOTIF. The behaviors and triggering conditions are used for analysis in the fault trees. Then, we improve the intended functionality by adding diverse sensors or more sophisticated cross-checking algorithms. By doing this, we are resolving the risk of overlooking an object and failing to brake. Chapter 2: Embedded Control Software. Once the architecture and the safety analysis are in place and the safety requirements established, we can create the application logic that will decide between autonomous mode and manual mode when the vehicle is in motion. Here, the autopilot is only allowed to be activated within a known geographical area, geofencing. But we could also make this decision based on road conditions, vehicle speeds, sensor confidence, etc., with the same architecture. We can perform all of the required software development, verification, and validation activities of this safety control with ANSYS SCADE and leverage the automatic code generation, which is qualified for ISO 26262 ASIL-D. Here we see the state machine, which indicates that the vehicle is in manual mode. If the vehicle senses that it is safe to switch to autonomous mode, the driver is alerted and a handover can occur. Once the handover occurs, we see that the vehicle is now being operated autonomously. In autonomous mode, SCADE sends a target position and other inputs to the ProCruiser planner, developed by Embotech, which in turn provides the driving path or motion trajectory to the control software. SCADE then provides the actuation of the vehicle. If we discover any requirements that do not make sense while creating the control code, we then alert those involved in the system's architecture and functional safety analysis stages. They, in turn, update the requirements, and the control application logic is then updated to meet the revised requirements. Here we have added a condition for pulling the vehicle over to the right lane and coming to a stop in case the driver does not take control when indicated. Chapter 3: Closed-Loop Simulation. Now, with ANSYS VR experience, let's test the entire closed-loop system in a simulation environment. VR Experience Driving Simulator, powered by Scanner, allows you to generate virtual environments by automatically importing road, logic, and objects from formats like OpenDrive, HERE, and OpenStreetMaps. We can bring an accurate vehicle dynamics model into the loop. It's quick and easy to generate driving scenarios based on the requirements defined during the functional safety analysis. The traffic can be auto-generated using the AI-based model, or you can select from a library of scenarios, including NCAP driving tests. Scenarios will typically be defined while performing the above SOTIF analysis. We will then use a smart way of varying scenario parameters to reduce the workload for simulation by orders of magnitudes. The goal of scenario simulation is to verify that perception, planning, and control algorithms are being tested to meet the predefined requirements. This will be achieved by using the world models, the scenarios, and sensor models. Sensors. In order to test the autonomous system, we utilize a scalable sensor model approach. We first start with semantic sensor models, which can directly output target lists for algorithms and controls verification. We then move to high-fidelity physics-based sensor models for radar, camera, and lidar. These can be used to validate how the perception algorithms would perform in different environments and under different conditions. Finally, to validate the full system, the complete AV software stack must be simulated as a black box. Multiple streams of sensor data must be fed into fusion, planning, and execution for virtual validation. All underlying cases are tested in an HPC environment by performing a parametric exploration, simulating everything in unison. We are now ready to bring the system, software, displays, and sensors together in our virtual environment. It's then possible to virtually test and improve the vehicle feedback according to the test driver's behavior and takeover time for digital, visual, and audio warnings. Optimizing human-machine interfaces with embedded software in the loop becomes fast and easy. The driver is in control of the vehicle as it travels through the city and is headed towards the highway on-ramp. As the vehicle enters the highway, the vehicle notifies the driver that autonomous mode is available and can be enabled. But humans can be slow to react, and through simulation, we can virtually test and improve the vehicle feedback according to the test driver's behavior and takeover time for digital, visual, and audio warnings. At this point, the driver enables autonomous mode. And the AV stack is in complete control of the vehicle. The AV stack collects sensor information that is fed to the control software. The software and planner are guiding the vehicle as it travels down the highway. It is easy to monitor situational awareness into the vehicle and the related human reactions, including the emergency management and the takeover efficiency, and to anticipate situations of foreseeable misuse. This motion execution happens in real time in a continuous loop. If the autonomously controlled vehicle leaves the safe operational design domain, then the driver is prompted to take back manual control. For example, the vehicle is now nearing the highway exit ramp, and the AV stack notifies the driver to retake manual control of the vehicle. The driver does just this, and the car is now manually controlled again. To ensure safety, the vehicle pulls to the side of the road if the driver does not take control when prompted. The car, driven manually, exits the highway. This approach has shown how to successfully ensure systems and software safety of autonomous vehicles through functional safety analysis, embedded control software development, and closed-loop system simulation.